My name is Sarah Lichtman. I'm a senior engineering major.
I'm Alex Blake. I'm a senior engineering major.
I'm Katie Anderson. I'm a senior engineering major at Harvey Mudd College. So eSolar came to Harvey Mudd with a clinic project. eSolar has this big field of mirrors that they're trying really hard to point really accurately at this tower to heat the working fluid, because the more accurately the mirrors point at the working fluid, the more it gets heated up and the more energy that they can produce. So one of the things that hinders how well they can aim at the tower is wind loads. They think there's a strong possibility that different parts of the field experience different wind loads, and so they want a way to measure that.
This is our eSolar Heliostat, and this is what was provided by the company that has sponsored this project. And this device is meant to track the sun. You put the mirror on top, and then they have software that allows the Heliostat to track the sun and reflect the sun at a particular point, which is the top of their heating tower. What we've done with this in order to determine the forces on this device is put a puck sensor, and the reason we call it a puck sensor is because it looks like a hockey puck a little bit. And we put this force and torque sensor at the bottom of the heliostat, and so whenever the heliostat shakes or moves because of the wind, we can sense the forces on there. And these forces come out in 6 different voltage channels, so we have to record those, and so it goes to our wireless sensor node.
So we've got a couple of different power supplies in here, but essentially we've got batteries providing power to these wireless sensor nodes, and then we've got the actual the signal processing for the sensor. It needs to be powered from this 5 voltage source in here. The output from the puck sensor is plugged into one of these boards, and then these boards are connected onto the nodes. And this sort of scales the voltage so that we don't accidentally blow up any of our equipment, which is a good thing. So then we measure the voltages that are coming off of the puck sensor, and you can actually see them coming out on the screen over there. So when we push on the sensor, you can see the voltages changing on the screen.
And so what we do is we want to measure the forces at each particular position in its whole range of motion. So we sweep through its range of motion basically 6 times, so we can try to cover as much of it as possible. And then we can fit a function that takes out the gravity forces at any position that eSolar wants to have it at. So they can say, let's put our heliostat at 45 degrees elevation, 60 degrees azimuthal angle, and then since we've done this sweeping calibration process, we'll know what the values due to gravity are at those points. And then take them out so that we can just see the wind forces.
eSolar wants to know what the wind forces actually look like at different points in the field, and this will allow them to maybe re-engineer the heliostats so that they're less expensive in certain parts of the field that don't experience as much force, or they don't necessarily get stowed away when the wind gets high enough. And with this, they can be a more efficient plant. They can spend less money on each heliostat and make more money as a solar plant, and make this sort of concentrated solar power more viable than traditional power methods. And that would be really cool, to be able to see the work that we do go into design decisions that sort of change the way that power works.
They're able to solve complicated problems, which has been really great. They're enthused about our industry. This team delivered, and we can use this for the design of our product for customers. So we're absolutely going to use it. It's a pretty key part of our engineering.